In the last session, we looked at the origins of integration and how we can think of integration as, to an extent, the opposite of differentiation. We looked at how we could find the antiderivative, and I want you to continue to try and make these links between differentiation and integration by just thinking back to some of the rules that we use for differential calculus. So yes, we've used the chain rule and the product rule and equation rule. But we also, when we were first starting out, used a series of rules such as the power rule. Now, for integration, we have an equivalent for each of these rules. So to start off with, the power rule. So the power rule says that this symbol here means if we want to find the antiderivative of x to the power n with respect to x. So this is saying, how can we find a function such that if we differentiate it with respect to x, we will end up with x to the n? And at the end of the last video, this is pretty much what we derived. So we would say that we would need to take this number n and add 1 to it. So if this was x squared, then our function would have the component x cubed, because when you differentiate x cubed, you would get 3x squared. We don't want the 3 here, so therefore we would want to divide through by 3. And this holds in general for n. So if we put x to the power n, it's going to be 1 over n plus 1 times x to the power n plus 1 plus c. And we also looked at why this can't equal to 1, because this gives us a value of 0, which is therefore undefined. The constant rule, as with differential calculus, we also have a rule, constant rule for integration. It says this: if I have a constant value, if I integrate the constant value with respect to x, that means what will I end up with such that when I differentiate it, I get k. All I do is multiply k by x and add the c. And again, we can check if I find the derivative, this is just going to give me k, so I can check my answers. Similarly, with the constant multiple rule in differential calculus, we also have the constant multiple rule in integration. So if I have a function multiplied by a constant and I integrate that with respect to x, that's saying what will I end up with such that if I differentiate it, I'll end up with k, a constant, times a function. And the rule for that is I can just take out the constant, and then I would apply, I would find the antiderivative of the function and just multiply them together. And finally, the sum or difference rule, just like with differential calculus again, if I want to find the integral of the sum or difference of two functions, all I need to do is find the integral of the first function and add or subtract it from the integral to the second function. So those are for the basic rules for integration, which I will invite you to try now in these 4 questions here. So the first question is just going to be applying the power rule, which we also looked at last time. So that's just going to be 1 over 6 plus 1 times x to the power 6 plus 1 plus this constant value here, which gives us this. Part B is going to be the constant rule. So again, this is quite straightforward. Find the integral or the antiderivative of 4 with respect to t. Well, we just multiply it by t. 4t plus c, because finding the derivative of this is just going to take us back to 4. Question C is going to be the constant multiple rule. So we said here we can take out the constant and multiply it by the antiderivative of x to the power 5, and we can here apply the power rule to this. Which means we end up with a half x of 6 plus 3c1. Now, we don't know what c is, it's a constant term. So 3 times a constant gives us no more information than just c. So we just leave this as a constant value because we do not know at this stage what the constant value is. For part D here, clearly this is going to be the addition rule. So remember, we can find the integral of each function separately and add them together. And you can see that here that in fact we can then further use the constant multiple rule to integrate these. and we're going to end up with 3/5 u to the power 5 plus 2u cubed plus 2u plus c. For E, again, this is going to be looking at the addition rule. So I can just first of all recognize that the cubed root of x is the same as x to the power third, and then I can integrate each of these separately, add them together, and I end up with a half x squared plus 3/4 x to the power 4/3 plus c. So let's develop this a little bit further then. Suppose I've got a velocity function here. I can integrate that in order to find the displacement function here, such that c is some arbitrary constant. So the integral of the velocity function with respect to time would give me this function here for the displacement. And this is called the general solution for this. And it's general because we don't know what c is. C could take any value whatsoever. But let's have a look at this scenario. Suppose you're given some additional information. So you also know that for this particular case, this particular particle, the position at time t equals 1 is 6. If you're given this information, that actually enables you to find c. So I'll just invite you to try and think about how you might approach that, and then maybe just follow this through. So this is called the boundary condition. If we have this boundary condition, we can find c. So what we've got here is the displacement function, so t squared plus t plus c. Now we can substitute in, because we know that the displacement at time t equals 1 is 6. So we can say that 6 equals 1 squared plus 1 plus c, which enables us to solve for c. So therefore here we have a displacement function t squared plus t plus 4. And this is called the particular solution of the integral of 2t plus 1 with respect to t. And that is because we know the exact values. So I will now invite you to have a go at these three questions. So part 1, this is saying if the derivative of 3x squared plus 2x gives us if we have the derivative here, 3x squared plus 2x, and we also are told that f of 2 equals -3, find fx. So we've got to work backwards or actually integrate this function to find fx. So the first thing we can do is use the power rule to integrate this, and then the addition rule, and we're going to end up with f of x equals x cubed plus x squared plus c. We have this additional information here of f of 2, so we can say that f of 2, or -3, equals 2 cubed plus 2 squared plus c. That enables us to solve for c, which is -15. So therefore this is the particular solution. For part B, we're given that the function passes through this particular point, and we're given the gradient of the curve is this. So obviously the gradient is the rate of change of y with respect to x, so if we integrate this we can find the equation of the curve. So if this is in effect the derivative, we want to work backwards, find the antiderivative, which we can do by integrating this function. So again, express this as x to the power -3/5, and then apply the power rule, and that is going to give us 5/2 x to the power 2/5 plus c. Use the information we've got here for f of 32, enabling us to solve for c, which is 20. So once we've got that, the equation of the curve, or the function f of x, is 5/2 x to the power 2/5 plus 20. Question C, the rate of growth of a population of fish is given by this formula here. In this domain, the initial population was 200 fish. Find the number of fish at time equals 4 years. So we know that this is the rate of change of the population. So we want to integrate this. This is the rate of change of the population. We want to integrate this with respect to t to find the population, which is what we're trying to do here. Find the population at t equals 4. So if we integrate this, this is a constant multiple rule. We can rewrite this as t to the power half, and then rewrite that as 100t over to the 3 over 2 plus c. That's the antiderivative for this. We know the initial population, so when t equals 0, we can solve for c, which is going to give us 200. So therefore, the population function, the function for population is 100t to the power 3 over 2 plus 200. We can then substitute in t equals 4 to end up with the number of fish after 4 years as 1,000.